Welcome back, everybody. Today we're going to talk about U-substitution, but more advanced U-substitutions. What do we mean by more advanced? Well, there are U-subs that don't look like U-subs, but once you get used to them, you get used to that they are. For example, let me just write down an example here. The following expression. How would I integrate this? Well, there are many other techniques out there, and I want you to understand that. Today I'm focusing in right on U-substitutions and when they work with exponentials. Really, I'm going to play around with exponentials and logs and get you used to them. So what I see here is I have x e to the 4x squared dx. Now, how do I know it's a U-sub? I don't until I try it. If I try my U-sub and this expression becomes easier to deal with, then I can easily do a U-sub on it. I know that sounds weird. Let me walk you through it slowly. So the typical choice for the U when it comes to an exponential is the exponent. I gotta keep saying the typical because it's not always true. There are many, many examples out there that counter everything I say, and it's just called practice. You practice calculus until you get good at it, until you do thousands of examples and you see them. The typical thing is the exponent is your U. So there's my U. In my previous video you've watched, hopefully, on integration, so this is integration part 2, or I should say U-sub part 2, what you do is the derivative of U is du dx. The derivative of this side implicitly is 8x. You multiply the dx over. You might be saying, why are you doing that? Well, let me show you the path I take. What I do is I write down my choice for U. I chose my U to be the exponent, and that's why you see e to the U. The e represents the exponent 2.7, all right? The base 2.7, obviously. So we have e to the U. Now I need a substitution for dx. Well, look, I can easily get that substitution for dx by dividing over the 8x. Divide over the 8x, you have this dx substitution factor, is du over 8x. So there's my substitution for that. So I have a substitution here, boom. Substitution here, boom. X, well, that's just X. I'm bringing that down. It's kind of like an extra piece there. I want to deal with it now. Because as you saw in the previous video, and I'm going to stop saying previous video, I'm going to keep it true to this video, notice the X's cancel. You might be saying, why? Well, because X divided by X. If they don't cancel, it's not a proper U-sub. You're probably looking for something else. But the X's do cancel in this case, and they will in this examples, because we're working on U-sub with e's and logs. And so the X's cancel. I pull out the constant in front. Be careful about that. Think about that. What number can I pull outside of the integral? I always like to pull my constants outside. It is not 8. It is 1 over 8 is what I'm pulling outside. Integral e to the u du. Look how simplified that expression looks. The X's cancel. Again, they have to in a U-sub. The 1/8 comes out in front because that's 1 divided by 8. Nice. And then I'm left with a beautiful, simple integral eu du. You look up your formula sheet, you look up the calculus book. The integral of eu du is one of the easiest integrals in the world. The integral eu du actually turns into eu. And of course, always don't forget your constant plus c. But this is important, so I got to make this clear. This integral eu du turns into eu plus c. All right, that's very, very important. That is one of our integral formulas. So this turns into this. Well, we've integrated. All right, the integral sign dx just tells you should integrate. I integrated, and that's why the integral signs are gone. What's left? Substitution. That is the original variable of usage was x, not u. So what is u equal to? Look for it one more time. 4x squared. And so this is my original function. The cool thing I like to do is take the derivative, make sure it matches. The derivative of a constant is 0, okay? The derivative of a constant is 0. I don't see it up there. Please understand why you do an integration, anti-differentiation. You're doing it because that's the derivative of some function. And really, I think of these as bookends. They really say it's time for you to integrate. Find the original function where this came from. And I did, for the most part. I need to find c. In a future video, we'll talk about finding c for a few examples. So stay tuned for that. But right now, I just want to work on the antiderivative. It's called the indefinite integral because there's no bounds in some respects. So if I take the derivative of this, as you know and love, the derivative of this is to rewrite this expression times the derivative of the exponent. The derivative of the exponent is 8x, right? The derivative of the exponent is 8x. 8x times 1/8 is x. So what's going on here is, again, the U sub is undoing the chain rule in the exponential. The exponential derivative involves a chain rule. It's rewrite times the derivative of the exponent. There's a chain rule there. The U sub is undoing that. So what I would do again is pause this video, take a look at this board, zoom in, walk around, make sure you understand every little step. Because bottom line, this is the technique I use. It kind of flows through the same way every single time if it's a good U sub. And that's the thing I like. I like logic. I like to have logical answers when I go through things. Cool. All right, let's look at another one. And really, it comes down to practice. I can't state that enough. The only way you're going to get better at integration is practicing integration. So we just did an exponential. All right. Can we do another one? Sure, I don't care. We can do as many as you want. So we can have e to the 4x cubed. And for sometimes, it's not often, this is more like a thing to mess with people, you can put it on the back, 6x to the 4th. Typically, I write it in front of the e because that's how I was taught to write. My constants, my polynomials, and then my exponential and log at the end. Sometimes we do this just to show you you can. So let's say we have this dx. Let's say we have to integrate this. All right, how would I do it? The exact same process. And I got to be careful. Let me make sure it can be done because as soon as I saw that, it could not be done. Now this one can be done. So what do we got here? How would I integrate this? Well, this is what I would do. I'd pick my u, and it seems the exponent does work a lot of the time, so we're going to try it. Here's my u. Does it always work? No. I can't give you a 100% guarantee because there are so many other examples out there. So what I do now, though, is I follow my path. E to the u. 6x squared was not chosen, so it's just 6x squared. My dx, I need a match for that. So we go back over to my drawing board. That's 12x squared dx. Divide over, and I get dx is equal to du over 12x squared by good division. So there's my substitution for the dx. The variable of integration is now going to turn into du over 12x squared. Am I going the right path? Again, pause. Do the x squareds cancel? Yep. That tells me we went in the right path. That's why if you wind back the video, that's why I quickly changed it to an x squared to make sure the u sub did work. We are working on the u sub right now, and that's why I'm making it work, so you can see it. The next thing you should do is open up that calc book and look at the end of the chapter and just try all different techniques at the same time and see when is best for what. And it's just practice. But right now, the squares cancel. Awesome. 6 over 12. Push out in front, right? 6 divided by 12. Think of that as a division sign. 6 over 12 makes 1/2. So pause on the video anytime you need. Pause on the video to catch up with me, okay? 6 out of 12 is 1/2. The x squareds cancel. Booyah! And we're left with this. And once again, we're left with an integral that we know and love. If we look up the integral of e to the u to u, you get e to the u plus c. And last but not least, we resub back in our u, 4x cubed plus c, and we are done. Just like that. And I like to pause and say, honestly, if you took a screenshot of the first example, and now a screenshot of this example, they really are the exact same steps. If it is a good U-sub, I should figure out what good is. If it is a U-sub, it should flow like this very nicely through. And it's just a matter of practicing and seeing what choices you have for you and what are good choices for you and what are some choices that are not good for you. And how do you know when it's not a U-sub? You know when it's not a U-sub when it doesn't work. What do you do now? Go to other techniques. There are integration by parts, trig substitutions. There are so many other techniques out there you may use. We're working on the U-sub again. What I would do is pause the video again, check it out. See if you have any questions. Excellent. Wash and repeat. It's just practice, guys. It really comes down to practice. So now we're going to go off script a little bit. We worked on the exponential. Now, let's look at the log. What do you mean by the log? Well, let's check it out. If you have 3 over 2x plus 6 dx. Okay, so how would I integrate this one? So it's our first one doing it. So we want to take our time, go through slowly with this. What I see here is I have a denominator. With integrals, it's very hard to do anything with denominators. There are some tricks out there, but when I see a denominator, I often rewrite it as a power. It's just a trick. And I shouldn't say trick. It's just an exponent rule. You can bring up any denominator by negating the exponent. And that's what I did there. I brought up the denominator by negating the exponent. Okay. So the denominator's coming up, negating the exponent. Got it. Now what do? Well, now, honestly, I'd follow the path of my first video. It looks like a parentheses power. It looks like the u should be what's in the parentheses, 2x plus 6. 2x plus 6, which means the derivative would be 2 dx, and so dx would be du over 2. It seems simple. What's the problem, Dr. McCullum? When I do the substitution, let's check this out. This would be 3, because that's a 3 in the front, u to the negative 1, because he chose the inside of the parentheses to be u, and commonly, that's what you do. Common thing to do is pick the inside of the parentheses when you have powers. Dx is du over 2. My first pause moment, my first check moment, was kind of bring it down a notch. I looked to see if the other variable, I keep saying x because that's the variable of integration. If this was z's, I would look for z's, whatever the letter's choice, and I should change the letters in the next sample. But what I do is, I look to see if all the original variables have been taken out, and they have. Do you notice there are no x's left due to my substitution? That's awesome. It tells me I headed in the right direction, I think. And then constant, sure, I see 3 divided by 2. Let's pull that out. And so now we're left with, how the heck do you find the antiderivative of a negative 1 power? I mean, you can't just go add 1 here. You can't. You can't add 1. That makes 0. That doesn't make any sense, actually. That doesn't make sense. A constant doesn't turn that into that. So we're having an issue here, a moment of, what do you do if it's a negative 1 power? The answer is, open the calc book up, looked up, there it is. There is a function whose derivative is a negative 1 power. That function is the log function. So we just know it's kind of like a red flag. That's why I highlighted it in red. It's a red flag. When you see a negative 1 power, it's time to pull out the log. That is, this whole expression, not the constant, this whole expression turns into the log absolute value of u plus c. It's a direct substitution again. When I see integral u negative 1 du, I know I'm dropping in natural log absolute value of u plus c. It's a formula. This equals that. Boom. And to be honest, then I'm done. If that's the formula, my last step is always to resub back in, and we're done. So my final answer is natural log absolute value. And I keep saying that because I need you to put that in to make sure it's critically correct. 2x plus 6. You need to make sure you have the absolute value in your answer. So we have 3/2 natural log absolute value 2x plus 6 plus c is my answer. If you take the derivative of this, you would match up to there and know it works. The derivative of this matches that, and that's awesome. So how do I know the natural log was here? It's because of that negative 1 exponent. Any other exponent, I'm going to do the power rule on. I don't care any other number. No matter how ugly the exponent is, I'm going to do the power rule, add 1, divide by 1. Sorry, add 1 and divide by that number. This guy is negative 1. So if you add 1 to it, you get 0, and that don't make any sense. How can a constant make that be the derivative of it? So it tells me there's something special about the negative 1 exponent. And it is. It's all about the log. Because if you look up the derivative, it's all about the check, right? The derivative of this. What the heck is the derivative of a log? The derivative of a log is the derivative of the inside over the inside. And the derivative of 2x is 2. That cancels that 2. Over the inside. Notice 2x plus 6. Huh? The inside, 2x plus 6 is in my denominator. That kind of hooked me up to why the log was coming. So how do I know I'm going to do the log rule? Look for the -1 exponent. If it's any other exponent, go back to video 1. Video 1 on U-subs, any power, bring it to me. 1/2 power, 2.8 power, I don't care what the power is, we got you. If it's a -1 exponent, whoa, that's just a special red flag, right? You're writing down, all right, if I see an E, I do this. If I see a power, I do this. If I see a -1 power, I do this. And that's really what it comes down to is experience, practicing enough to see these. Cool. Let's do one more. Make sure we wrap it up nicely for you guys. The good thing is if you've watched these 2 videos back to back, and my future videos, because there's going to be more coming on integration, there has to be, got to practice this. When it comes to integration, there's a logical path, and once you get used to the logical path, it's the same thing over and over. But then, you know, we like to mess with your students. As students, we like to mess with you a little bit. So let's say we have e to the x over the e to the x plus 1 dx. Let's say I have this integral. Oh my, what's going on? Well, you know, why not? You just got to hold true to the rule. Well, you could try. Ooh, let me let u be x. If you let u be x and work your way through, you end up no simpler than you started. Just change the letter, really, of integration. All right, that didn't work. Is there anything else, Dr. McCullough? Ooh, I know, don't do any bad algebra to me. All right, let me cancel the e's. Ooh, don't make me come through the TV or whatever you're watching me on right now. All right, that's bad. Ooh, don't do that. If this expression was flipped upside down, I think we could do that then. That's algebra, that works. The problem is the 2 terms in the bottom is what seals them together, and that's why I saw something sneaky. I saw the fact that those 2 terms were linked together, and so I could bring them up with a -1 exponent. You can always bring a denominator up as a -1 exponent, right? Denominator comes up, poof, -1 exponent. And then, how do I know this is the right path? I don't until I work it out. I really don't. I check my u. My u is typically the inside of the parentheses. The derivative of u is du dx. I multiply the x over quickly. Du dx is the derivative of u. Go back to your implicits if you don't see that. The derivative of e to the x is e to the x. Aha! ex dx. Ex dx. Yep. So what we got here is I would bring the ex down just to keep the logic, right? Make this u to the -1 just to keep the logic. Make this, what would that be? du over e to the x. Let me make sure I got that right. Because you would solve for dx. That means it's du over e to the x. Cool. This matches this. That's perfect. Notice what cancels. The e to the x's cancel. Whoo! Boom! Drop the mic. The e to the x's cancel. That's why, how do I know it's done? Well, I'm the guy making up the problem, so I knew it was done. How do I know? Through many, many versions of these examples in life is why I knew that was going to happen. And so I have u to the -1 du, and there I am. Again, the e to the x's cancel. They're gone. I'm left with u -1 du. That's your base formula you can find in any calc book. That means my answer is the natural log absolute value of u plus c. That is exactly the formula I'm talking about. This is our formula from a formula sheet or a calc book. The integral of u to the -1 is natural log absolute value of u plus c. And then last but not least, you plug in what the u is, ex plus 1, and you are done. And this is my final expression. All right? The natural log absolute value of ex plus 1 plus c is my final answer. Again, if I wanted to, I could take the moment to take the derivative of this. It would match up there. Because remember, that's what integration is all about one more time. The integral, that's your derivative. This is the original function plus a constant. So we just go back and forth with the practice of that. Over and over we practice. This is our second video on U-Sub, and it just comes down to practice. Are there typical choices? Yeah, there are typical choices. If I see a parentheses power, I pick the u inside. And that's really what I'm holding out to. Parentheses power, u inside. I was looking forward to the power rule. In this case, the power is -1. That's not a power rule. That's a very special rule. That's like the, right, again, the red flag rule. You see the -1? Oh, they threw the red flag. It's the natural log rule. boom. And that's what it is. You just got to get it in your head. You see a -1 power, booyah. Natural log is what it turns into. Now, why did I not pick the E? I did quickly, actually. I picked the E, the exponent of the E, that is. I'm sorry. The exponent of the E. That's U. Well, that doesn't get much, because that's U over U, and there's nothing. It doesn't simplify. It just looks like that. So really, there's nothing to do in that expression if I let U be the exponent of E. It doesn't go anywhere, really. So, another beautiful U substitution. Excellent, guys. So, in summary, the best thing I could do right now is look at a summary board. And what I would like, make sure this board stays put, is, let's see, we have the following. And we'll bring that E back. If I have e to the x plus 3 over e to the x, that's not a U-sub. That's algebra. How do I know? Practice. How would you know? Practice. Really, it comes down to. That plus means I can split it into 2 fractions. And really what I have is 1 plus 3e to the negative x to integrate. I'll leave you to think about how the heck I did that. E to the x over e to the x is 1. There you go. 3 over e to the x is rewritten as 3e to the negative x. And then I would do each one of these separately. Now, how do I know it's a log? Well, because an example that starts out as a log like this, that is a log, with my u being there, and when I bring it up, I get a -1 exponent. So that right there is why I know it's a log, is because of the -1 exponent. But something of this expression I can quickly change into a non-log, going back to our first video, just by doing the following. I could take the exact same fraction, but add an outer exponent of 7, or whatever number you want. And then, once again, I see a fraction. We don't do fractions and integrals, so we rewrite them. There are a few cases. Always, whatever I say is never guaranteed. It's best practice. What I typically do when I see a fraction, I mean, there are trig subs. If you're into trig subs, woohoo! You get a trig sub. Or, or you could try rewriting it first. All right? There are other techniques out there. I need to make you understand. I go after the U-sub. Well, I go after algebra first. That's good old algebra. Then I go after the U-subs. This U-sub will work. Notice they're very similar. The only difference is this U-sub leads to a log. This U-sub leads to a power because the power is not -1. The power is -7. What would you do for this one? Well, I'd expect you to follow my videos and go through and get your answer. If you add 1 to that exponent, it's now -6. So your final answer will have some power of -6 in it. This guy, because it's a -1 power, turns into the log. Again, that -1 is the red flag. That's the key. This is a good old power down here. No issues down here. It's good old power U-sub. This guy is a log. Absolute value. Because of the fact it is a -1 exponent. That's really what I'm summarizing here. You see a -1 exponent, you're going to have to turn that into a log because that's the rule. You see a power that's not -1, any other number, I don't care. It's going to be a power rule. I can add 1 to -7, it's -6. All right, the power rule can work on anything else. It's just that -1 you got to be careful of. Why did I put this over here? Just so you see, sometimes it doesn't have to be a U-sub. It can be simply good old algebra. You can always, if you have 2 or 3 terms in the numerator, you could split the denominator. That's just a technique of algebra. You always have your algebra up your sleeve, and as I'm moving around through my videos. But yes, exponentials are typically U-subs. I'm not going to deny that. If I see 8x e to the 3x squared dx, that's a U-sub. That's straightforward, right down the middle, U-sub. The reason I know is I've gotten used to the derivative matching. There is a derivative matching game in my head I'm always doing. The derivative of 3x squared is 6x. Oh, the x. Ah, there's a cancellation. in the U's and the DU's. There's a cancellation technique that I keep using over and over. Why? Because I've done thousands of these through the years. And it just comes down to practice until you see it, right? Can't hit a fastball until you've seen it many, many times. And that's the same thing here. This would be a U-sub on that, and you would get your final answer if you walk through my video slowly as before. Thank you guys for watching this video. Please stay tuned for more.